All right, so last class we talked about Euler paths and Euler circuits and how to find those and when certain graphs have an Euler path or an Euler circuit. Today we are going to talk about Eulerizing a graph, which means adding edges so that you can create an Euler path or an Euler circuit. You might think, what's the point? Well, it depends on what you're trying to find. So in a lot of applications of graph theory, each edge represents either time or money. So if you cannot create an Euler path or an Euler circuit and you have to retrace your steps, that means it is either taking you more time or costing you more money to finish the route, whether we're talking the mailman, the trash man, whoever it is that is traveling this route. So we want to make sure that we add the fewest number of edges possible to make sure that we are not taking too much time or spending too much money. So this is called the optimal exhaustive route. So we are going to be retracing our steps or adding extra edges as few times as possible. So this whole process is called Eulerizing a graph. So the basic idea for Eulerizing or the Eulerization of a graph is you need to find all of the odd vertices, add some extra edges so that every vertex is even, and then you can create an Euler circuit. Because remember, an Euler circuit has to have or can only exist in a graph that has all even vertices. So let's take a look at these two graphs here. First, we need to go through and write the degree of each vertex. All right. Now we need to find our odd vertices, which there are two on each side of our graph. And we want to add some extra edges that connect our odd vertices. So now I've added an extra edge here. Now the degree of both of these vertices is 4. So I can repeat this process for the other pairs of odd vertices. And now we have a graph with all even vertices. So we have Eulerized this graph. It is now possible to find an Euler circuit. Let's look at this again. At the next graph, we're going to write the degrees of each of the vertices. Now, again, we have odd vertices on the outside of this graph. So we are going to duplicate some edges so that we no longer have odd vertices. Now, we can add an edge here, just like we did on the previous example. You might think, well, this seems like the right thing to do here. We can connect these two odd vertices. But one of the rules of Eulerization is you cannot create an edge between two vertices that are not already directly connected. You can only add duplicate edges. Okay, so I cannot add an edge here connecting these two odd vertices. But I can duplicate both of those edges, and now I have vertices with degree of 4. Okay, so this whole process of Eulerization, you can only duplicate edges. You cannot create new edges between vertices that are not already adjacent vertices. All right, so now we can continue duplicating edges. Again, here we run into the same issue that we had on the other corner. I cannot directly connect these two odd vertices, but I can duplicate these edges. So now I have a graph with all even vertices, so I can create an Euler circuit through this graph. Right, you might notice that it was a lot easier to Eulerize the first graph than the second graph. You have to retrace your steps a lot more in the second graph to be able to complete an Euler circuit. Now, what if we don't care about an Euler circuit? What if we only care about an Euler path? We don't have to start and end at the same place. It's going to be a very similar process, except we can leave two odd vertices. It doesn't really matter which ones you leave. That'll depend on which vertices would require the most extra edges. So again, you want to minimize the number of extra edges that you have to add. So it is the same process. We are going to start with our graphs, identify the degree of each vertex, add some duplicate edges until we only have two odd vertices. Okay, so these are the same graphs that we had earlier. So I'm just going to rewrite the degrees of each of the vertices. So it doesn't matter which vertices we choose to leave as our starting and ending points. I'm going to go ahead and leave these top two odd vertices as my starting and ending points. So I'm going to add an edge here, an edge here, and an edge here. All right. So now I have what is called a semi-eulerization, where I now have a graph where I can create an Euler path. I cannot create an Euler circuit because I still have two odd vertices, but because I only have two odd vertices, there is an Euler path through this graph. All right, let's look at the second graph here. Again, you want to write the degree of each of the vertices. Okay, so again, we need to make sure that we choose the best option for our starting and ending points. So I'm going to show you one way to do a semi-Eulerization of this graph, and then I'm going to show you a better way. So I'm going to choose these two vertices as my starting and ending points, meaning that they are going to stay odd. So then I'm going to add duplicate edges to the rest of the graph to make all of the other vertices even. Remember, you can only duplicate edges. You cannot create edges between vertices that are not already adjacent. So here I have done a semi-Eulerization of this graph, and I'm going to count how many extra edges I had to add. 1, 2, 3, 4, 5, 6, 7. So I added 7 extra edges. Let me show you a better choice. If instead I had chosen these two vertices to be my starting and ending points, all right, I now have a semi-Eulerization with 1, 2, 3, 4, 5, 6 extra edges. So this is actually better than the original semi-Eulerization that I had done. So in general, you want to add as few extra edges as possible because each edge either adds time and or cost to your route.